The cofactor approach to finding the determinant of a matrix is it's very similar to the big formula that we just discussed in the previous video, but it is done in a recursive way that is far more digestible, if you like, and it allows for some interesting properties of the determinant to come out, and we'll see those in the videos tomorrow when we talk about applications of determinants. To give you a feel for what the cofactor formula is, we'll revisit the 3x3 determinant that we just saw in the previous video. So let me start by writing the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so this is a general 3x3 matrix, and I want to find its determinant. Now remember, matrices, the important property in both the big formula and the determinant by cofactors is linearity. And remember that a matrix has linearity in each row separately. So even though I will start by explaining this for the first row, it actually works for any row and any column. And I will show you more of that in practice. So I'm going to describe the general case only for the first row, but then I'll apply it for different rows and different columns in examples, because that's how things become easier. Okay, linearity in the first row says that I can split this row into a sum. As long as I keep the second and the third rows the same, I have a sum of determinants. So I can write the following thing. I'm going to use my specialty here to copy stuff. Oops. Well, I hope it worked. No, it didn't. To make life a little bit faster. Okay. Because I'm going to need 3 of those. Well, I better move it. All right, so I copied the matrix 3 times. You'll see why. I want to represent a sum here. Now, of course, this is wrong. I can't write this. I just said the determinant equals 3 times itself. But what I can write is I can write zeros here, then 0 here, and finally zeros there. So now the sum of the first rows in the 3 determinants here, so this row plus this row plus this row equals that row. Linearity allows me to write this. Now, I can continue by linearity of the first column and try to split this up because linearity works for columns just as it works for rows. Remember, the determinant of A being equal to the determinant of A transpose means that all the rules I have for rows also are there for the columns. But we know with a little bit of combination of the properties that I can eliminate under this row. And because of the zeros that are here, even though I haven't written them, I know that I can eliminate these 2 terms without affecting this part of the matrix. So elimination on this matrix would produce zeros here, whereas these terms will stay the same. In the second matrix, if I take the first row and I eliminate with it, even though that's non-standard, we would like to eliminate with something that is in a pivot position, but still, that doesn't mean we cannot carry out elimination. What it means is that I can take this term and eliminate underneath it without affecting these 2 terms and without affecting these 2 terms. So what I see is that the determinant does not get affected by these terms. I could just remove them. Similarly, in the last matrix, I can use that first row to eliminate with it underneath, and that will eliminate this term and that term, and I will be left with matrices that don't have components here, here, or here. Now remember, this corresponds to in the previous video, we talked about choosing A11 and then nothing else from that row and nothing else from that column. Well, that corresponds to this matrix over here. And then we said, well, I could choose this. And if I made that choice, I would need to choose this, or I could choose this term and then I could choose that term. Now, in a 3x3 case, you may feel like, why stop here? Why not continue? But the idea is that I can do the exact same approach with arbitrarily large matrices. And all I have is, if the matrix is n by n, I'm going to have n many submatrices. All right. Why is this important? Well, the idea of cofactors is that now the first determinant actually equals A11 times this smaller determinant, A22, A23, A32, A33. So I have a bigger determinant expressed as a sum of smaller determinants. From the second one, now I don't really have a plus sign, I have a minus sign. I have minus A12 times A21, A31, A23, A33. And I'll show you where that minus comes from. The next one is a plus. A13, so I factor that 1, 3 out. And then I have determinant of the minor. A21, A22, A31, A32. These submatrices are called minors. They'll have a notation. So because this is the minor of A11, so we'll denote that as M11. We'll denote this as M12, and we'll denote this as M13. Okay, what about the minus sign? The key to understand here is actually this matrix. Why the determinant of this matrix equals the determinant of that matrix? And the answer is quite simple, really, because you see, you could, so we've eliminated here, okay? Now, how do I calculate the determinant in a known way? Well, I need to continue the elimination, right? I have to take this pivot, eliminate underneath it. That would change this pivot. And then the determinant will be the product of the pivots. Well, the first pivot is A11, and then the other two pivots are right here. So I could say it is A11 times the determinant of that matrix, which is going to be the product of the second and third pivot. So now that we have convinced ourselves that these two things are the same, how can I get to this? Well, remember, whatever applies to the rows applies to the columns. So what I have is this matrix, A12, A21, A31, A23, A33. You understand everything that's empty is just a bunch of zeros that I'm not writing. What I could do is I could switch the first two columns. But when I do that, I have to change the sign. So I have minus A12 and then A21, A31, A23, A33. Now, since we convinced ourselves for the first matrix, we know I have to keep that minus sign, but this is minus A12 times A21, A31, A23, A33. And you can use the exact same trick for the third matrix. Now, to get what you will need there is you will want this to be a third column and this to be a second column. So actually that requires two column exchanges. First you would exchange these two columns and then you would exchange those two columns, and so you have even number of column exchanges, which will guarantee that you in fact have a plus sign. Now, you don't have to play these tricks to figure out the signs. What you, the way to remember it is that you always look at the matrix, the signs, if you like, are -1 to the power of I plus j, where I and j indicate the row and column of the number. So 1, 2, I is 1, j is 2, 1 plus 2 is 3, it's an odd number. -1 to the power of an odd number is -1. So if you look at the matrix here, 1 plus 1 is an even number, so that gives you plus. 1 plus 2 is an odd number, that gives you minus. 1 plus 3 is an even number, that gives you plus. 2 plus 1 is odd, minus. So you see you have plus, minus, plus, and then from this plus, continue minus, plus, minus. Then I can continue down, plus, minus, plus. You see the signs have to alternate. So again, plus, minus, plus, minus, plus, minus, plus, minus, plus. They always alternate, with this one always being plus. So I can't always say that the last term is plus or minus because that has to do with the size of the matrix. Well, actually, I can't say because these two numbers are the same. So this is always even. So you can always start in the bottom if you like, plus, minus, plus. But if you have a 2 by 2 matrix, this is plus, that's minus. So the last term in the first row would be a minus, whereas in a 3 by 3 matrix, it would be plus again. So here we can just quickly think plus, minus, and so on. Then from that plus, I keep minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus, and so on. So to recap, this is how we get the signs. We can do this expansion. So this is called expansion along the first row because the sum of these three rows is the first row here. I could have done this along any row or any column and it will still work. The key here is how to write this formula because I promised a cofactor formula. So we pick a row or a column for a general matrix, and then we call these submatrices minors, whereas the determinant of the minor, including the appropriate sign, is what we will refer to as cofactors in the expansion. So here's the cofactor formula. Of course, I hope you don't have to memorize the cofactor formula. You've already understood it and you know how to apply it. But it goes like this. So you can expand along any row, and that is written in the following way. The determinant of A is given by AI1. So this is the ith row, expansion along the ith row. AI1 times the cofactor I1 plus AI2 times the corresponding cofactor, plus AIN times the corresponding cofactor IN, where each cofactor includes the correct sign. So each cofactor, Cij, includes its correct sign. Namely, Cij is minus 1 to the power of I plus j times the determinant of the minor ij. How do you get the minor ij? So if you have the matrix A, right, here, and you take, say, the ith row over here and the jth column over there, here you will have aij. You get the minor by removing the jth column and the ith row. So what you're left with is the minor mij. So on this side, once you remove the jth column and the ith row, you get the minor mij. Whether it comes with a plus minus or minus comes from I and j, and the cofactor is actually that complete determinant, including the sign. So the cofactor formula is exactly this for any row. I could also write it for any column. So this is expansion along the ith row. So you see the determinant of an n by n matrix is the sum of n determinants of matrices of size by one lower. So these cofactors, they're all of size n minus 1 by n minus 1. And this is what we call a recursive formula, because then to compute the determinant of mij, I could use cofactor expansion yet again. So let me write the cofactor formula with expansion along the jth column. So cofactors down column j. So the formula is the determinant of A equals A1j C1j plus A2j C2j plus ANJ CNJ. Okay, so the point is you can either use expansion along along a row or along a column. When are cofactor formulas useful? They're useful when your matrix has a lot of zeros. Otherwise, you get way too much to work with. So let me give you one quick example. So let's say we want to calculate the determinant of 2, -1, 0, 0, -1, 2, -1, -1, 2, -1, -1, and then a 2. So maybe I'll put those zeros. Now here, what are some good choices for an expansion? The first row is good, the last row is good, the first column and the last column are all equally good. Why do I say that? Because the formula for expansion contains, so what are these? What is A1j, A2j, ANJ? Those are the entries in the jth column. So if, say, this entry is 0, I don't really have to look at that cofactor, right? So here, if I do expansion along the first row, then I have this number times that cofactor with the correct sign, plus this number times the corresponding cofactor, plus this number, which is 0, times the corresponding cofactor. But who cares about that cofactor? I've multiplied it by 0, and then plus 0 times that cofactor. Again, because I'm multiplying by 0, it doesn't play a role. So really, when I apply the cofactor formula, I'm going to do it, in this case, expansion along the first row. So because and you do it only along one row, you don't do it along more than one row. The first row, the first column, they're convenient because of the signs. I know I have to start with a plus, minus, plus, minus. Of course, the last two don't matter. So I have plus and minus for the components. And the way I write it is 2 times a smaller matrix. I eliminate that row and that column, so I'm left with this matrix over here. So I have 2, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 2. Then I have minus coming from over here times negative 1 times the corresponding minor of removing the first row and the second column. So I will have negative 1 and then this part over here. So I have negative 1 and then that's it in the first column. In the second column, I have negative 1, 2, negative 1, and in the third column, I have 0, negative 1, 2. Okay, so I see that this minus negative 1 becomes a plus. Now, the interesting thing here is we can actually come up with a formula. So imagine this matrix was going bigger and bigger. Let me call by D4, let me label D4, the determinant of this 4 by 4 matrix. Okay, now you see this matrix over here has the same pattern except that it's 3 by 3. So let me label that D3. And what about the last one? Well, I have this is the matrix with the same pattern of size D2, but this matrix is not that. However, if you think about expansion along the first column, you see that the determinant of this matrix is minus 1 times the determinant of that matrix. So I see that this over here is minus 1 times D2. Putting it all together, I get a formula for the determinants. D4 equals 2 times D3. And then let's be careful with the signs here. So this is plus 1, minus times minus is plus, but then I have that negative 1, so it's actually minus D2. The interesting thing is that you can use this expansion to come up with such a rule. This is what's called a recursive relation or rule. Why is it important? Because I know exactly what D1 is. I know that D1 is just 2. So knowing D1, I also know D2, right? We actually need to compute D2 as well because the relation contains the previous 2 numbers. It's a little bit like a Fibonacci sequence type. So the determinant of D2, well, that's very easy, right? If you just focus here, you have 4 minus 1, that gives you a 3. So we have that this equals 3. And so knowing these two, I can immediately find D4. Then if I know D4, I can find D5, then I can find D6 without actually computing determinants. So that's pretty neat. Well, actually, when we talk about eigenvalues and eigenvectors, I'll show you how to solve these things immediately so that you know what the nth number is. But it can be proven that the nth number will give the formula dn equals n plus 1. Now, I haven't shown you that this formula holds in the nth case, and I can do that right away. So let's generalize this, this problem where we have the dn, right? So I have 2, negative 1, then I have negative 1, 2, negative 1. Then I have, so you see what happens in the pattern is that this diagonal continues all the way, then this diagonal continues all the way, and then this diagonal continues all the way. So that's what that matrix looks like. Perhaps I need one more row here before I continue. So I have -1 here, a 2, and a -1. All right, so I'm going to do expansion along the first row. That says I have 2 times the smaller matrix, right? I remove the first row and the first column. That is exactly the same matrix with the same pattern, only the smaller size, right? So maybe I can just write here dn minus 1. And then when I go to the second term, I remove the first row and the second column, and I get minus -1 times the matrix -1 with zeros underneath, and then I have -1, 2, -1, and everything else continues, right? I have a -1, 2, -1, and so on. They continue. So I know that this new matrix is of size n minus 1 by n minus 1 because I removed 1 row and 1 column from a matrix of size n by n. And so expansion along the first column in this matrix says that the determinant of this matrix is simply -1 times the determinant of that matrix. You can make the same conclusion using pivots. So this would be the first pivot, and all the other pivots will be present in this submatrix over here of size n minus 2 by n minus 2. And that matrix has exactly the same pattern as a dn, except it's smaller. So again, we come to this 2dn minus 1 minus, the reason for the minus is that I have minus times minus, which is +1, and that minus comes out. So I have minus dn minus 2. So just this matrix is of size n minus 1 by n minus 1, but this matrix is n minus 2 by n minus 2. So we have the formula in general terms where we can compute the determinant of the nth matrix through the determinants of the previous two smaller sizes. So this recursive relationship is very important and it comes up very frequently in computer science, for example. So computers would love such a relationship where you don't really have to compute determinants. The pivots also give us a formula, but this is quite convenient. Now, one final thing that I want to show you before we are done for today is just how to use the cofactor formula in a matrix where we don't exactly want to expand along the first row or the first column, for example. So let's say we have this matrix. 1, 2, 3. I just want to have a bunch of zeros maybe here. 0, 1, 0, and then I'll go, I guess, with a 4, 7, 3, 2, 5, 4, 11, 2, 1, 1, right? Not the prettiest of matrices. You can do well, actually, let me make it uglier. Let me make this a 3. So we kind of really don't want to do elimination here, right? Because I have to work with that 3. I'm going to have a bunch of fractions. Can I make my life a little easier? And the answer is yes. I could do expansion along the third column. Why would I choose the third column? It's got 2 zeros. So I don't have to worry about the minors that come from those zeros. I just have to worry about the signs of the numbers 3 and 1 that are in the third column. So what I'll do is I'll first fix the signs. I need to know the signs. I start from the beginning, plus, minus, plus, minus, plus, minus. So I see that this 3 and this 1 come with plus signs. Their minors will come with plus signs, or their cofactors will come with plus signs. And then I just have to write their respective cofactors. So what I have from the formula is 3. So this 3 times, because of the plus, so that's already taken care of, I don't have to worry about it, times the determinant of the minor when you remove that row and that column. So whatever is left goes into the minor, or the cofactor. So the minor is the matrix, the cofactor is the determinant that includes the sign. So here we have 7, 5, 2, 3, 4, 1, 2, 11, 1. Then if this was not 0, I would have gone minus that number times the respective cofactor, but it is 0, so I don't have to worry about it. The next one I go to is that 1, so it's plus 1 times the determinant of whatever is left once I remove that row and column. So I have plus the determinant 3, 7, 2, 2, 3, 1, and then 4, 2, 1. Now I can use the formula for 3 by 3 matrices, right? Especially if I have a calculator, that's particularly useful. I don't really want to use elimination on a matrix that looks like this. The numbers aren't pretty. It's going to take me a long time if I'm doing it by hand. Computers would actually always do that. So at this point, you can continue with further expansion, but you can also continue with the 3 by 3 formula. So how do we do that? I will continue here 7, 3, 2, 5, 4, 11, and I'll do the same for the next matrix. So here I have 3, 2, 4, 7, 3, 2, and I will have my diagonals. So each matrix will have 6. The diagonals that point to the right will come with pluses. Those that point to the left will come with minuses. So I'll do that simultaneously for both determinants. Right? There we go. And so here I have 3 times. I'm going to open parentheses because I have a bunch of pluses and a bunch of minuses. Along the first row, along the first diagonal, I have 7 times 4, which is a 28. Plus, along the second diagonal that points to the right, I have 5 times 1 times 2, that's a 10. Plus, I have 2 times 3 times 11, that is 66. And then I have 3 that come with minus. So minus 2 times 4 times 2, that is 16. Minus 7 times 1 times 11, that's a 77. Minus 5 times 3 times 1, which is 15. We're done with the first matrix. Then the second matrix, I'm going to put a parentheses. It's not necessary. I'll just do that for visualization purposes. So the first diagonal that goes to the right is 3 times 3 times 1, which is a 9. Plus 7 times 1 times 4, that's a 28. Plus 2 times 2 times 2, that's an 8. And then minus 4 times 3 times 2, so that's 12 times 2, that's a 24. Then 2 times 1 times 3 is a 6. Then 1 times 2 times 7 is 14. And I will leave the simplification to you, but this, on a test, you can also use a calculator. That would be fine. But I do want you to show the work. So please do not use any software to solve these things. I actually need to see the process if you want to have full marks. Okay, well, that is that from determinants. Please do some homework and we'll see each other tomorrow or hear each other.